Practice exam 3, problem 33. The effective nuclear charge is the positive nuclear charge experienced by the valence electrons after taking into account the shielding from the inner core electrons. The effective nuclear charge explains many of the periodic properties that are observed. Now here's the question. Which of the following properties are consistent with an element having a high effective nuclear charge? Now let's review what penetration and shielding are. Okay, so you see in the nucleus, you have protons. All are positively charged. And then electrons carry negative charge. All right? So therefore, the electrons are attracted by the nucleus, precisely speaking, attracted by the protons. All right? But there is a problem for the outer electrons, or the electrons in the outer shells. So the attraction between those outer electrons and the nucleus is weakened. There is a shielding effect, you see, so which means if they go further in, that's called penetration. But you see there are inner electrons or core electrons. So electrons, both they all carry negative charges, then they repel each other rather than attractions between electron and the nucleus. Okay? So that's why the inner electrons are considered as the shielding. Okay? So the ones that shields the nucleus, so that weakened the attraction between outer electrons and the nucleus. Now let's review what effective nuclear charge, ZEFF, is. Okay, so basically this explains the penetration and shielding. Okay, so the ZEFF can be calculated using the atomic number, so we can call that actual nuclear charge, subtracted by the shielding electrons, so the inner electron. Now let's take a look what is asked again. Okay, so which of the following properties, we're talking about those different properties, not elements, all right, are consistent with an element having a high effective nuclear charge. Okay, a high effective nuclear charge, ZEFF, again can be calculated by Z minus S. S basically is the number of the shielding electrons. So, or in other words, the core electrons, the inner electrons. Okay? If we take the elements in the same period, let's say the third period, okay? If we take elements in the same period, they should all have the same number of core electrons, which equal, in this case, equal 10 electrons what neon has. All right? So in this case, the S is fixed, so that should be 10 for all of the elements we just talked about in the third period. Okay? And now, as you can see, the S is fixed, then E is directly proportional to Z. All right, the higher the Z, the higher the effective nuclear charge. Now our focus is to find, okay, anything related with the atomic number. Okay? And now let's take a look at those three choices, okay? Actually, those are three statements, not choices. The choices are here. Actually, there are 5 of them. Okay, first, low ionization energy. Now let's take a look what does low ionization energy mean. If you look at the periodic trend for ionization energy, in the same period from left to right, the ionization energy increases. Then low ionization energy means the atomic number is lower than the others. So therefore, if the atomic number is lower, then the ZeFF is also lower. So therefore, this one will not, whatever the elements having this kind of property, would not have a high effective nuclear charge. Okay? So now let's look at the second one. A small atomic radii. Okay, a small atomic radii. Atomic radii or ionic radii, they have the opposite trend compared with ionization energy. Okay, so the smallest, so smaller radii, smaller size. Okay, so since it increases from right to left, all right, it increases this way, then it decreases. The smaller one should be on the right-hand side. Okay, so you see the smaller one, the ones with the smaller atomic radii does have higher atomic number. All right, so you see that's increasing radii, then decreasing radii, smaller radii is this way. So therefore, the atomic number actually increases. So from that sense, this one would deliver this result. Okay, the smaller the atomic radii, the greater the Z, and then, of course, the greater the effective nuclear charge. Third, a highly negative electron affinity. Let's take a look at the chart again. Okay, so this is a negative electron affinity. You see, it increases in the same period from left to right, which means here, again, like chlorine, that should have the highest one among this group right here. We are not talking about the noble gases, okay? So, and now, look at the atomic number, of course, always increase from left to right in a periodic table, all right? So, therefore, a high negative electron affinity, high, which means goes this way, high negative electron negativity, affinity translates into higher Z value, higher atomic number. You see, from left to right, again, it goes higher, 13, 14, 15, 16, 17. If Z is higher, ZeFF is higher. It means we would have higher effective nuclear charge if an element has highly negative electron affinity. So both 2 and 3 can deliver this result, can have a higher ZeFF. Now look at the choice. 1 only, no way. 2 only, no. It's not just 2. 2 is good, but it's not just 2. 3 only? No. Yeah, 3 would meet this condition, would deliver this result, but it's not. but not just 3. It's 2 and 3. D, 1 and 2, obviously, that's also wrong because 1 is the opposite twin. E is the only correct choice.